So, when the official title is RG flows for chiral rings and BPS spectra, but much of what I'm going to say is based on paper called Constant RG flows. And I will mention a few further thoughts on the subject probably for the second half. So there will be also something outside of it. And the framework that we're going to discuss is pretty much following the footsteps of the previous speaker. We'll talk about renormalization group flows and constraints on this basic and crucial phenomenon in particle physics and beyond that unfortunately I don't understand very well, where we undergo quite dramatic transformation from one sort of physics to another, albeit the corresponding theories by T, so there'll be TUV and TIR, assuming that these are nice, well-defined theories. Renormalization is some sort of flow that connects the two, and sometimes the character of the theory or physics associated with it changes quite dramatically, so that you may have completely different spectra of particles, Lagrangians. You may not even see the fields that you have in the UV in the IR, so everything may change. And these plus lots of other facts motivated many people to think that Feynman diagrams that we often use to do computations is not the right way to do quantum field theory. So actually, the reason I'm giving this entire talk is partly because I don't understand quantum field theory 101 that I have been teaching for almost 10 years now. I don't really know what I'm doing, so I have no clue. And the goal is to understand, well, hopefully, what quantum field theory is, and perhaps this will be a little tiny step toward perhaps reformulating it or saying something beyond standard Feynman diagram. So the way this, I'll start with a bunch of questions. I'll list lots of questions, and then I'll try to knock off at least half of them in the talk, and then hopefully the other half will motivate all of us for discussions, further thoughts, and so on. So first question, which is already suggested kind of by this title, is suppose you have two fixed points, two conformal fixed points, TUV and T infrared. Is there a way to go from one to the other in multiple ways? And if so, are there these different paths related, or do they have anything to say about each other, and so on? So first naive question is, how many RG flows are there from TUV to T infrared for two fixed theories? That's one natural question. Another question that I guess is kind of suggested by this picture is, where does this picture belong? When we draw something like this, that there is a path from TUV to, from one theory to another theory. Is this path on the blackboard? Is this path in some abstract space? And some people call it theory space, but honestly, every time I've heard the word theory space, whatever it is, in previous talks or wherever, I usually fall asleep because I have no idea what we're talking about. Well, I should put quotes and question mark outside and perhaps frame it as a question. So what is this theory space is my second question. Very naively, it is space of couplings but the reason I usually fall asleep or couldn't follow much of discussion that involves this concept in any serious way, because I don't really know. Like, is this really a space? Is it Hausdorff? Is it smooth? Is it finite dimensional? Is it infinite dimensional? What are we talking about? So, smooth, Hausdorff, and so on. I mean, luckily, many questions that I'm going to frame here are kind of connected to each other. So, and as I say, there will be some answers as well. So it's not that I'll be listing questions for half an hour and there will be no substance to it. But it's good to have lots of questions on the list to discuss them. So then, the way, so suppose Feynman diagrams is not quite the right approach to quantum field theory. And again, there are many indications to that. So they come from completely different directions. Sometimes you want to compute a certain quantity, you sum over zillions of Feynman diagrams, and then with a simple answer, which it clearly begs for much better derivation or explanation. So there might be a new mathematical framework. But then we should ask what things in quantum field theory we're willing to give up on, and which things we want to keep as a sacred part of quantum field theory. Anything observable, obviously, we want to keep, because that's part of physics, that's why we are doing this. Something that's intrinsic, like, again, Feynman diagrams themselves, probably have to go. And suppose, again, there is another mathematical framework to quantum field theory. It has to describe some sort of physics via degrees of freedom, and that's where this notion of number of degrees of freedom usually comes in. And there are various ways of defining it and measuring it, and especially is relevant to questions like RG flow, precisely because we have no idea what happens here in this intermediate shaded region. That's a big question mark, a big mystery. If there is anything or something that we can keep track of globally, not just in the vicinity of fixed point, but throughout RG flow, and perhaps compare between UV and infrared, that would be useful piece of information. So one such quantity, which was already discussed in the previous talk, is C function. So there you saw that there is indeed a notion of, I'll call it C function, not A function, which takes the theory of T and assigns to it some number, in general perhaps real number, but maybe integer if it really counts number of degrees of freedom, or some sort of fractional number, maybe positive or negative, but again, positive typically if you really think of number of degrees of freedom. So another, this sort of question is very broadly defined, and I'll try to make it a little bit more precise. We'll break it down into sub-questions, each of which will be completely different and worth of studying. Namely, my motivation here is to ask what are the various quantities that may express the number of degrees of freedom along the RG flow and be compared between the fixed points. So if you're thinking about skiing downhill from here to here, so you obviously lose something, you'll lose altitude and perhaps your skis and other things. So typically you expect that you come out here with less degrees of freedom, skis, poles, whatever you lost along the way. And the question is, what are these skis and poles in quantum field theory? So what are the different characteristics that can describe the entire process without the crutch of Feynman diagrams or anything intermediate, which again, many people believe is only intermediate to our calculations. So then next, or actually even here, comes the whole point of this C-theorem conjecture package, so which I have to review. So there are three versions of this C-theorem conjecture. And I'll review for you what the conjectures are, what the variants of the conjecture are, and then the status in each dimension. So there'll be a nice follow-up on what we've heard in the previous talk. And the first version, so this is kind of sub-bullet point, makes a statement only at the fixed points. So the statement here is that so it is called weak, first of all. So this is weak statement of the C-theorem, or conjectured C-theorem, that at fixed points of the RG flow, which here I call TUV, TLR, could be lots of others, C of this value of the function in the UV is larger than the value of the function in the infrared. So next version is stronger. Here. And this now requires knowing that this C function exists along the entire RG flow. The first version didn't require the C function to exist everywhere. You would be just comparing its values at two endpoints. But if it does exist along the entire flow, then the statement would be that its derivative of this function as a function of theory is parameterized by little t, which many people think of as RG time. So here's another cartoon here. This is t. I'll call it RG time. And the flow itself can be described as some sort of trajectory from TUV to infrared. So then this derivative is less or equal than 0. And moreover, at fixed point, beta functions vanish. So I could call it lambda star or T star, where star refers to fixed point. And this should be equivalent to the statement that d CDT is equal to 0 at the fixed point. So that's a slightly stronger version. Again, the main point is that just like this graph suggests, in fact, what I didn't specify, the vertical axis can be vaguely thought of as the height function, this C function, where it makes sense that every intermediate point, which again didn't have to be the case in the weakest version of the C theorem, and it basically decreases as we fall. Okay, so then the next step, and the last in this hierarchy of different conjectures or versions.
So just to be clear here, you don't have any particular C function in mind. You're just asking whether there exists a
Yes,
C function.
yes, exactly.
Clearly, if one exists satisfying either of these things, then an infinite number exists. So
Exactly.
it's just
Exactly. It's right. It's a question of fishing for meaningful functions at this point, and then it's, we're not going to worry about uniqueness. We're going to worry about existence.
So are you worried if this flow is reversible, for example, you can go back up, or you assume it's not reversible?
Well, that's why this questions about C functions are extremely useful for even asking this question, because yeah, so if it exists and satisfies this condition, then obviously it is reversible, because there is some quantity which decreases as you crank up the flow.
It is what?
Irreversible.
No, I mean, reversible means that I'm at some point and I can go up, so I can integrate back the degrees of freedom in a unique way.
Oh.
So if I can recall, or many trajectories cross and I cannot unintegrate. I mean, Wilson defined it in irreversible because you integrate out.
Right.
But in quantum field theory, you can go like this or you
Right.
can go back up with
Right.
new.
So I think if I understand the question correctly, then the answer is that you can go back up in infinitely many ways, and there are, right, so we'll talk about this, but the answer is definitely not unique. Because there are many theories which flow to the same infrared, and I mean, that's, yeah, you're losing degrees of freedom integrating something out. So if you integrate in, you have lots of choices what you integrate back in.
But maybe your theory space, whatever it is just big enough so that
I mean, in quantum physics you have lambda of mu, and you can do mu below or mu up, like in QCD you go to UV and you claim that you are doing.
if you're at any
Going
point
to the
that's not
UV
a fixed point in your theory space, and you not give you a derivative, that there's just a single flow.
But there are lots of functions which, again, at that point
No,
we
I'm
have to
just saying that
specify
there's
what we're doing. I prefer, and throughout the talk, I'll mostly try to ask global questions about fixed points. So to me, nice flow is which has beginning and the end. If we're talking about these questions, we would have to ask, you specify just one derivative, lambda of mu, two derivatives, and then I'll play all the tricks. You give me two derivatives, I'll find you a function which matches up to two derivatives, and they're different than the third derivative. And there will be some field theory interpretation of that. I'm not sure with what kind of high order operators and stuff like that. Now people talk a lot about resurgence and instanton effects, which is even worse in a sense that it also has to do with situations where you have functions which match as power series to all orders, and yet they're different non-perturbatively, meaning at e to the minus something minus 1 over coupling constant corrections. So again, we can play this game, but that's a little tangential to what I'm going to say. In any case, I think even locally with that picture, there are non-unique ways to integrate it back in. So, but it will depend on how much data you provide to me, and there'll be always a way out. Okay, so where was I? So there is a stronger version, and finally there is the strongest version of this theorem, which says that for G flow is actually gradient flow for this function C. So what I'm going to explain, and that's one of the goals of this talk, is to show that if you apply, so if you take this statement and put it in the machinery of so-called Moore's plot theory, then it says that if the strongest form of C theorem holds, then there is another characteristic, I'll call it mu, which behaves very much like a C function, and in the UV it counts degrees of freedom in the sense that it's greater or equal than mu at the infrared, where this mu is defined as number of relevant operators O in your theory, at least at the fixed point. Either this, so this implication means that either this holds or else we lose the smoothness. So basically some of the assumptions that go into this statement fail. It means that certain smoothness has to be lost along the flow. And one can interpret this as a statement of some sort of phase transition. After all, when we lose smoothness in physics, if some function is discontinuous or its derivatives, something is not smooth, we usually call it a phase transition. And extra credit problem for me will be to explore what kind of phase transition it is. And I don't know the answer to this, but at least I'll show you some phenomena which point in this direction. Okay. We'll poke at it, but it will be much later. So, in that sense, in a sense of obeying similar inequalities, this function mu can also answer the question of what possible degrees of freedom are. And one can refine the question even further. In supersymmetric theories, where we have supersymmetries and supercharges, we can explore analogous variants. So here, if, again, I have to describe to you a lot more what this statement means, but if there is any chance that some number of operator count will behave like number of degrees of freedom, why don't we just count supersymmetric operators in supersymmetric theories? So could it be a measure of degrees of freedom? So one such notion is chiral ring. There are two closed things, and one is chiral ring. It's defined as a set of all operators O in your theory which are annihilated by supercharge, QO equals 0, or possibly QR equals 0, modulo those which are Q bar or something else. And one natural question you can ask is there any notion or any sense in which chiral ring in the UV is bigger than chiral ring in the infrared? So that's again yet another question, maybe number 5 or 6 in my list. Yes.
So are you counting these by saying that there's some algebraic structure and it's the number of there's a linear structure and there's some number of dimensions and then it's suddenly dropping in dimension from one dimension to another?
You mean dimension of the ring?
Yeah.
Something like that. Here I'm very vague. It's
Okay.
literally at the beginning. So, and that's a great question. So what exactly do I mean by this inequality? So perhaps a better way to write it, and with my handwriting, well, it's actually quite similar. So it may be that this ring is contained in that. That's a mathematically better statement. This allows to deal with infinite finite rings, and but it may happen that it's not really contained, but still smaller in some sense. And again, we would have to address this kind of questions. It just, I want to point out at something which is very funny situation where these rings are bread and butter of what we do in, say, supersymmetric quantum field theory, at least from the formal point of view when we analyze it. Any statement we can say about supersymmetric theory is usually just a statement about chiral ring of some sort. And yet we never ask this sort of questions, how chiral rings differ in the UV and the infrared in a sense of containment, and so on and so forth. And once we start thinking about it, it will force us to ask completely different class of questions compared to what we normally ask, and then that's in some sense the goal of this. So it will prompt me in a direction which is in some sense uncharted territory, and again, only half of it I'll be able to say something about, and half I'll be glad if any of you have thoughts or ideas, because, yeah. Anyway, so another version of this question is in terms of states. So normally we think that there is, at least in conformal theories, there is a nice state operator correspondence, and this chiral ring is made out of operators which are nice with respect to supersymmetry. They're killed by supercharges and so on. Likewise, in the spectrum of states, there are special nice states called DPS states, which are likewise annihilated by some supercharges. And we usually consider this modulo Q applied to some other state. So you can ask if, again, spectrum of such DPS states, which is certain part of the Hilbert space, in the UV is larger than in the infrared. So that's yet another question. This sounds pretty abstract and bizarre, and a priori not even related to these other questions I asked, but I promised you that they're all intimately related. So I had no interest, for instance, in studying chiral rings and this kind of questions. But even thinking about this sort of statement will force us to think about it. So they're interrelated, and if I have time, I'll actually make some precise statement about each of these questions, even including these two. Again, I don't know the full answer, but I'll offer partial answer. Okay, any other questions so far? So this is, I guess, the list of questions that will serve me as a motivation, and I'll try to gradually say something.
So if you have marginal directions, where do they show in here?
Yeah, so let's I promise to answer to that, but let's hold it. So in fact, I'll make a note for myself. So marginal. Yeah. They'll be nicely part of the story, but I'll be able to address it maybe like in half an hour. If that's okay.
For this definition of your mu function, it doesn't bother you that there are theories that are not empty, but for which mu is 0?
No, it doesn't. Yeah, it doesn't. For example, a good example of this is actually what Al pointed out to me half a year ago. The monster CFTs is an example in 2 dimensions. Yeah. And again, depending how we count this function, for instance, or Juris-Douglas theories may be an example. So there are quite a few. It's not.
Yeah. They have relevant definitions.
Well, again, depending how you count it, but some of them are, there are non-trivial theories which are just endpoints of the flow. Yeah. And they don't have supersymmetric relevant. Okay, any other questions? So the idea here is to come up with this set of functions or rings or whatever else, gadgets, which may say something about the difference between UV and infrared in terms of number of degrees of freedom. So these are very unconventional C functions. They're not C functions in any reasonable sense, but they behave very much like that. So this count of relevant operators, these rings, and again, as a homework, I can suggest think of your own one. So tonight, at the dinner, for instance. Okay. Now, let me start gradually unraveling the story and demystifying it. So, again, most of the time I'll try to focus on this function mu, and then toward the end, either if I have time, it will lead us naturally to these questions, or maybe I'll just mention it briefly. Regardless, we'll talk about other things. So if we talk about the function mu, then it's natural to call this as some sort of mu theorem, which is not necessarily the statement that it's decreasing, but it's this binary statement that it's either decreasing or we lose smoothness, so in that form. So let's try to see, can we easily come up with counterexamples just from everything we know so far. And I'll use this as an opportunity to summarize again what we know about C theorem, now in this refined sense, different forms, weak, stronger, and strongest version, as well as possible counterexamples to this statement about mu behavior. So let's start in 2 dimensions. That's obviously the easiest. Where we know that weak and stronger versions of the C theorem are proven. So that's Zamolodchikov. And stronger version, sorry, strongest, the statement about gradient flow, I'll say believed to be true. I guess the statement reflects the fact that no one has real doubt about it, but if you ask, has it been proven rigorously, then the opinions diverge and depends on who you ask. So for instance, there is a very nice work of Friedan and Konechny where proof with various assumptions was proposed, and some people consider it final word in the story, some people consider it as a first word in the story. So as far as the strongest statement about gradient flow goes. But I think almost everyone would agree that it probably holds there. Now, the reason I want to work, one way to look at this behavior of mu is the following. So kind of turn things around. Think about it as possible topological obstruction, if you wish, to the statement of gradient flow. So gradient flow usually for us means that it is indeed like a nice flow in the space of couplings. In order to define it as a gradient flow, you typically need some metric, definitely some sort of smoothness, and you even have to derivate things because you need to take a gradient. So you need a space, you need reasonably nice space. If it's non-Hausdorff, as I speculated in the beginning, it wouldn't even make sense to talk about gradient flows. So this is definitely the strongest and the nicest form of life, if this is really what happens in quantum field theory. Now, it's hard to prove that something doesn't exist, because suppose you look for this C function, you define it as some anomaly coefficient, and you find that, okay, it doesn't satisfy gradient flow. Okay, that sucks. But then you go and look for another option, then you check, oh, this other option looks actually nice, and it agrees with number of degrees of freedom at critical points, let me try that. Again, it may even decrease along the flow, but it's not gradient flow. Then you say, aha, it came really close, because maybe now I can try to modify the metric on my space of couplings and force it to be gradient flow. And this process never ends. So the question is, instead of checking it one by one, and that's actually how you do it in practice, because you have certain nice candidates for the C function, usually. How can you possibly know if this strongest form is supposed to fail? If it's supposed to fail, you're not going to check infinitely many functions with infinitely many choices of metrics on a theory space. You want some sort of topological obstruction. Great. And what this statement does here is it allows you to say, yes, there is an obstruction. either way, one way or the other. And either you lose smoothness, which again is something where it wouldn't be nice gradient flow in the first place, or this has to hold. So for instance, if you find that mu behaves in a funny way, you already know that it's not going to be nice gradient flow according to that. So that's why that's a way to probe and have a topological abstraction to nice vanilla light. Okay? So therefore, when I summarize for you what's known about the strongest form of the C theorem, it's convenient to keep in parallel discussion of whether we know any counterexamples to such statements where this can possibly happen or not. And in all two-dimensional RG flows, and again, there are plenty because two-dimensional CFTs are in some sense better studied than anything else, we always have mu of TUV greater than mu of T infrared. The index changes in the direction you expected. There is no counterexample to this, but there is also no proof. And my point in this talk, or at least part of the talk relevant to this behavior of mu, is to correlate these two things. To say that behavior of this strongest form of the C theorem is actually related to behavior of this count of relevant operators. So if you have a situation where you believe or have no counterexamples of this type, you should expect the strongest form of C theorem and vice versa. If you have violation of this inequality, that's a hint that the strongest C theorem should not be true. Like kind of serve, you'll use it as a probe or topological abstraction.
So this is greater than or equal to?
Yeah, that's greater than or equal to precisely because it's related to this marginal count. Yeah. So
like if you're looking at a renormalizable theory, it's equal. Is that the idea, or?
No, it has nothing to do with renormalized. I mean, yeah, it has to do with yeah, with the count of marginal operators. How we exactly define this. Yeah, because relevant means that their scaling dimension is less than dimension of space-time. But if I put here less or less than or equal, will make a little difference. And it's actually important to get some things right, but I don't want to spend, it's at this point, it's irrelevant detail, no pun intended, but I'll get to it when I give the answer to the promised marginal. Okay, so now this is story in d equals 2, at least as much of the story as we'll need. And again, in all other dimensions, I'll try to make a correlation between behavior of this count of relevant operators along the flow versus gradient flow or smoothness. Now, in dimension 3, again, the opinions may be different, but at least my personal one is that there is no compelling candidate for the C function in the first place. So not only we're lacking any sorts of proofs of all these C theorem conjectures, the weak, the stronger, the strongest form, we don't even know for which C function we are supposed to check them. And there was one which was on the market for a while, then it branched off in several subtle versions, and again, it's very far from being made into any sort of reasonable statement. So here, the world is widely open, but we'll see this pattern in the sense that in a spectrum of dimensions between 2 and 6, which is what I'm going to go through, dimensions 3 and 5 are very odd, that we have very little control over RG flows. In particular, I don't know anything about behavior of this mu in 3 dimensions. Now,
So when you say there's no good candidate C function, you mean something that exists along the flow?
that exists along the flow, and I included in my, say, stronger intermediate version of the C theorem condition that it's stationary at the critical point, so that's why it's. Okay, D
But
equals.
for the weak version, in D equals 3.
Well, again, there's this long debate about you can define a 3-sphere partition function or various versions of C function by entanglement entropy, but as far as I know, there is no proof.
There's at least a candidate for a weak version.
Well, there is a candidate for the weak version, but yeah, there is no proof. And honestly, this candidate again lacks many other nice properties. That's why I myself would not bet much money that that's the right one. But again, it depends kind of whom you ask, but the story is, as you can see, much worse than in 2 dimensions. And then the same is going to be to some extent in 4. So reaching the 4-dimensional case.
Do you have anything to say about the mu?
No. Likewise, yeah, here I'm just collecting everything I can find about behavior of these relevant operators and searching hard. I couldn't find any counterexamples, but again, we know very little, so that's why I don't know if it's indication that there shouldn't be any violation or just lack of understanding of 3- and 5-dimensional theories or insufficient ones. Okay. D equals 4. So here, we have nice candidates. In fact, we've heard about this A function in the previous talk. So the weak and stronger version have been proved by Komargotsky and Schwimmer. There is no proof of the strongest version of C theorem, and it's kind of has been a suspect. If you ask opinions of people, and thinking about it, I obviously had to, say in 2 dimensions, almost everyone would agree that in 2D, we believe that gradient flow, that RG flow is a gradient flow. If you ask the same question about 4D, you'll see that the enthusiasm will shift down. How down, it depends again who you ask, but it's definitely not as obvious and less likely. There is no counterexample, and that's part of the reason I started thinking about it, because again, if you're supposed to disprove the statement, how do we disprove it? Or what's the topological abstraction? So that's supposed to be 1. And yeah, so the strongest form is open. And here I want to suggest that it's unlikely to be true, in a sense that you're not going to have nice, smooth gradient flow throughout, because there are examples of flows where mu goes from lower value to high value. So this goes by the name of dangerously irrelevant operators. And examples I know are in n equals 1 case. And if there are sufficiently many of them, then what you have is mu of in the infrared may be bigger than mu in the UV. And then, according to this statement, the corresponding flows would not be nice, smooth gradient flows. So maybe this is a good time to make a quick remark about general remark of what we call relevant, irrelevant, and marginal operators.
And just to be clear again, here you're counting, in this case, n equals 1 supersymmetry preserving.
Correct. Yeah. So in a CFT in general, you can define the spectrum of operators by analog of the Hamiltonian, which is the scaling dimension. It's basically eigenvalue of the dilatation operator. And you get some discrete spectrum, so it could be various states at various points. Then the value where scaling dimension equals dimension, space-time dimension of the field of the theory is very special. That's where you have a distinction between operators which are relevant and irrelevant. So this part of the spectrum is spectrum of irrelevant operators, because if you add them to the Lagrangian and start initiating the RG flow, they don't affect where you go. They basically, their effect dies away. But these guys here are relevant. And this middle line consists of marginal operators where conformal dimension or scaling dimension is equal to dimension of space-time, which is 2, 3, that's the D's that I'm going through. Now, there is a lower bound typically. So there is a value of delta, which I'll call delta minimal, and it depends on space-time dimension D, below which no operator can have its scaling dimension in a unitary conformal field theory. So this is often called unitarity bound. So therefore, when I describe this band, I should really go from delta minimal to this marginality condition. And what happens in a typical conformal field theory is that you have infinite spectrum of operators. Of course, you can take products, fields, and so on. And because scaling dimension is additive, you can build easily operators and fields and states of arbitrary high scaling dimension. But typically, this band is occupied by finitely many members, and this one contains the infinite piece. So in some sense, this count that we described here is a reasonable count because in, say, nice isolated theories, it typically is some finite number. You can just enumerate it. Basically, you look at the lowest part of the spectrum, which is what intuitively we want to do anyway when we think about the spectrum. Okay. Also, what happens is that if you start with this kind of spectrum and try to go with RG flow, which I'll describe by this RG time t. So you start in the UV spectrum, which will be composed of, say, oops, yeah, it could be that something that sits here, something like this, and you flow to the infrared, then what's going to happen is that this spectrum will change somehow, and because it has, you know, lower bound, it has nowhere to go below. What you would typically expect is that everything goes up. It would be very funny if things, you know, start oscillating. So if they go somewhere, they have infinite room to go up, but only finite room to go down. So therefore, what happens typically in most of the RG flows and theories is that you have this kind of behavior. So what this picture illustrates is a typical renormalization, a very standard procedure, which is a phenomenon, typical renormalization where conformal dimensions go up and sometimes they go down. And it is this funny trajectory which started life as irrelevant operator in the UV and suddenly got into the relevant range at some point along the RG flow, and it is this guy which is called dangerously irrelevant operator, it is dangerous because if you didn't know that it's becoming relevant at some later point, then you have ambiguity in kind of initiating the flow, because you could have some admixture of this guy, and it could trigger where you go in the end. So we'll talk a little bit about it. It's not ambiguity in a strict sense of this is not turned on, but it's ambiguity in a sense of you end up with relevant operators that you didn't see in the UV. And how do you know that you suddenly have new relevant operators, new dimension, new directions to continue the flow? So you would have no access to this in your UV theory. And that's the ambiguity.
So you probably know what I'm going to say. So to object to this whole picture, I'm not really sure what you mean by the anomalous, the spectrum between two fixed points.
I totally agree. Yeah, and
so, and I also think that a clearer definition I would propose for dangerously irrelevant operators have to do with the global structure of the flow, which is what you alluded to, and not this question of, which seems, I'm not even quite sure what it means, of an operator somehow crossing through marginality.
yeah, exactly. So let me, I totally agree. So this is just a cartoon. That's something to keep in mind. And I'm not even going to discuss why I myself don't like this picture. There are many reasons, but there is a lot of truth about it, and there is a lot of, again, points where one has to not even worry, where I don't even think that that's quite the right description. The main one being that scaling dimension is not even defined. In the intermediate range, there is mixing. There are lots of things going on. So that's why I like to make statements about comparing this index mu at beginning and end, which is definitely well defined. I just wanted to give an intuitive definition of what dangerously relevant operator means.
The number of space-time dimensions can change in infrared to the UV also. You can have 4-dimensional
That's possible. That's also quite interesting. So the way, it's possible to incorporate that very easily. You just think of theory in the lowest possible dimension that you have. Typically that's infrared. I know very little about RG flows which have oxidation of dimensions. But then you write everything in terms of fields in the lower dimensional theory. And it basically will say that you have infinite spectrum of KK-like modes describing the UV physics. That's the way to think about it. But it can be easily incorporated in that framework again with additional bells and whistles.
Do you have any simple toy model or example of your dangerously relevant operators?
Yes, I'm coming to that very slowly. So here I mentioned that I managed to find one in supersymmetric world, and perhaps so let me maybe complete this table, and then I'll answer this question. So that's actually quite along the lines I'm going to describe for you. So here, in fact, it's convenient, and even in 4 dimensions where we still are so far, to classify everything according to amount of supersymmetry. If you have n equals 4 supersymmetry, which is the largest, then there are no interesting RG flows, so you can just do them by hand. So I'm going to discard that by case very quickly. So basically, it ends up with n equals 1, n equals 2, and n equals 0. And I mentioned that in n equals 1 case, there are such dangerously irrelevant operators, so there is this violation. So therefore, I would strongly suspect that the strongest form of the C theorem does not hold. In n equals 2 case, conjecturally, this doesn't happen. There are no such dangerously irrelevant operators. And this is due to work here. This is beautiful Cincinnati. And that leaves essentially n equals 1 case as the only controllable case where I know such examples. I don't know any non-supersymmetric situations where this would happen. And even in n equals 1 case, it's actually hard to find them. So another conjecture could be that they don't happen, period, so that you never have dangerously irrelevant operators in any theory. I don't know, I would be very skeptical if that's really the case, so I suspect they can be. So this is quite possible. But they're really hard to come by, so that's part of the reason I'm giving you this summary. In fact, this is the only item in this whole big, long list, summary list, where I managed to encounter such examples.
Yeah, like in your running this cartoon picture, if you start from irrelevant range and go to like in the IR, if you go to marginal, you still call it dangerous irrelevant?
It still is interesting. I mean, part of this is let's study things which are unusual.
Oh, okay.
So it still would be very interesting.
So there are some non-supersymmetric possible example of such operators, like in so-called walking theories. If you take psi-bar-psi operator, it's a fermion bilinear. In free field theory, it has dimension 3. So in the old days when people worked on walking theories, the idea was that this psi-bar-psi operator, the scaling dimension would go from 3 to 2 when you consider the walking limit. It's like approaching something like the Van-Zaks fixed point. Now people have been doing simulations of these kind of theories recently, and then they see large anomalous dimensions, I think of the order of 1. If it is 1, then it becomes from, the scaling dimension goes from 3 to 2. And then, so
What dimensionality?
Yeah,
is
what
the
space-time dimension?
space-time is 4.
Oh, but that's well within this range.
Yeah.
So,
Then,
okay.
then it looks like it's just becoming relevant to more relevant.
But maybe then psi bar psi squared, for instance.
Psi-bar-psi
could-
squared.
Yeah,
Yeah.
could be
That's
exactly.
the operator.
I'm sorry, so you're saying
Yeah.
6 to 4.
Yeah, so psi-bar-psi squared goes from 6 to 4 or less than 4.
Good.
So that's basically what's needed for building models.
I would love to hear more about it.
Okay.
And I'd love to again explore what evidence there is. So as I say, unfortunately, by scanning through a lot of literature and asking people, and again, that's part of the reason giving it here, I would appreciate any sort of input about. So now you can see my attitude. I'm interested in weird renormalization group flows, weird where something like this happens. So this is basically the only class of examples where I could find it in a relative abundance. But I have to say it's also based on conjectures of things like Seiberg duality, which again we haven't proven. So therefore, even here, it should be taken with a grain of salt. And even here, I try to get rid of all weird phenomena which may also happen in n equals 1 physics. And something I couldn't get rid of is moduli spaces. So not only these theories involve lots of marginal operators in the UV and in the IR, which will make the definition of this index mu somewhat delicate, they actually involve whole moduli spaces. And that's something that from this perspective is even more tricky. So in some sense, I want to point out, yes, there are such examples, but do I again trust them where I would put everything on the line? I'm not so sure.
So you're only interested in flows from a conformal fixed point to a conformal fixed point, is that right? So, for instance, Rahana's example started with the UV theory actually was UV incomplete because it has an irrelevant operator there, and then he was wanted to say that it flowed in the infrared. If you allow examples like that, it's easy to write down many examples of dangerously irrelevant operators.
Yeah, but that's indeed, I have much less to say about it. So I really want fixed point and classification of complexity of the fixed point is that isolated fixed point, meaning no marginal operators, is by far the cleanest. Minimal models on 2D, something like some of the Argyris-Douglas type theories in 4D n equals 2 are vanilla examples. Next come free theories, theories with marginal deformations. but no moduli spaces. That's next layer of complexity. That's a little easier to incorporate. Basically, you replace some of the strict inequalities by non-strict inequalities. And last come theories which are either free, have free components, or moduli spaces of vacua. And those are much, much harder because in that sense, in certain sense, they have mu equals infinity. And then controlling that is more difficult. Because you can initiate infinitely many flows. Okay, so slowly going through this table. So let me get to d equals 5. Here, if n is equal to 0, namely it's non-supersymmetric example, again, very little is known. Again, I don't know any examples of or statements about dangerously irrelevant operators in either d equals 3 or d equals 5. So I have very little to say about that in general.
What would you say about monopole operators in 3D? If you try to find them in the UV, it's not strictly speaking a CFT, but in a sense they are very relevant there and sometimes become...
Right. I have to, yeah, so let me not try to think on the spot. Again, I prefer really to start with a fixed point, but that's a good example. So maybe we can cook up a nice fixed point.
Or to cook up a transaminase.
Exactly, yes. And then, yeah, we would have to analyze it. So let me not try to do it right away. Okay, so then next case is n greater than 0. So if you have a supersymmetry, in fact, minimal supersymmetry or higher, then not only you have no dangerously irrelevant operators, you have no relevant operators. So that's thanks to your work.
5D?
Well, claim,
No,
claim that you have both 6D and 5D.
In 5D, they're relevant operators.
Supersymmetric
Yeah,
ones.
they're mass deformations associated with flavor currents.
Okay, so then I guess, so I'll scratch that statement, and I'll transfer it to d equals 6 version. But there is a d equals 6, right? So you would agree with that?
Yes.
Okay, so d
I
equals
hope so,
6.
because I said it before.
No. Again, as I said, I know little about d equals 5 and d equals 3, which is clearly reflect. So here, again, if you have minimal SUSY or higher, then there are no even relevant operators to study interesting supersymmetric or G flows. So therefore, what this whole picture now illustrates, again, after we finish the summary, it's becoming very boring if dimension is very high. It's also becoming very boring for a different reason if dimension is too low. So the picture is like this. In 2 and 6, it's something too simple. Probably wild things, crazy things, or interesting things don't happen. In 3 and 5, again, we just don't know much, so I can't really say anything. But then it picks up in 4, where these weird behaviors may happen, at least potentially, and that's the general picture here. Yeah.
Here's a quick question. Do you have any claim or statement about the strongest version, the gradient flow version of the C theorem, implying a statement that the endpoints of the flow are actually conformally invariant rather than scale invariant?
No, I don't think so.
You don't want to make such a claim?
No.
Because then there will be very clean counterexamples of that.
Right, and then thank God I didn't claim anything like that. No. In fact, it may be a good point to give you some motivation for where this mu statement comes from. And again, I want to emphasize, partly answering the previous question, that this n=1 examples are the only ones where I know there is potential danger in a reliable, almost reliable way. And again, it's important to say almost, because even here it hinges on certain conjectures and facts about SUSY gauge dynamics, which is necessarily strongly critical. I want to point out that even though, I mean, for instance, you object to this global picture, and so do I, but it is still a good cartoon for the following reason. When, again, we teach QFT, we do talk about anomalous dimensions. So this spectrum of deltas is definitely reasonable, close enough to each of the fixed points. And here I want to give one intuitive piece of evidence for this just from basic physics, and why things may be so boring in 2 and 6 and peak out at 4. See, if you think about how anomalous dimensions behave, if you have interactions which are Yukawa type, superpotential or potential interactions, they typically tend to crank the anomalous dimension and the for-scaling dimension up. If we have gauge fields, they typically, again, there are maybe various counterexamples, but generically, they may push things down. So therefore, this type of behavior really is easier to find if, again, you're trying to find such counterexample where anomalous dimension would be negative now, in theories which have a lot of glue, a lot of vector type interaction. In 2 dimensions, there are no interesting vector bosons, gauge degrees of freedom. They're all either topological, non-propagating, or you can replace them by scalars, whatever else. So in 2 dimensions, in some sense, there are no vector gauge bosons. And that's roughly part of the reason why in conformal perturbation theory in 2 dimensions, typical behavior that you see is these guys going up. But as far as I know, even in 2D, where again we have conformal perturbation theory, where there are so many things we can know and analyze, nobody has actually studied derivative of scaling dimension and its sign. So it would be natural to follow what Samolochikov did and try to constrain the sign of derivative of delta and relate it to certain positivity or negativity. But again, that hasn't been done. But I hope that this comments about anomalous dimensions help you, A, to keep in mind why this picture is a reasonable cartoon. Again, it becomes murky in the interior, but again, our whole quantum field theory becomes murky in the interior. And secondly, it says that near the boundary it is true, and it gives you kind of a hint why in 2D you don't really expect why many people believe that's the case. Okay.
So can I ask a naive question about the marginal operators again? I just had in mind things like what we do with ADS-CFT, where you look for BPS states at weak coupling and a strong coupling, and some of them get lifted. So sometimes, usually, what you say is there are less BPS states at strong coupling than at weak coupling, but that's just a marginal flow in between there. Is there any way to know why there's more on one side than the other, or is there a general way you can say how many states get lifted under such marginal flows?
I'm not sure I understand what marginal flow refers to.
So if you just take n equal to 4 Young's or the ADS3 kind of
Right.
ADS-CFT things, you can compute the number of BPS states through an elliptic genus at weak coupling.
Yeah.
And if you go to strong coupling, you find that there are actually less BPS states than at weak coupling. Some of them pair up and get lifted.
Right.
Is there any way to put a mathematical structure on how many states get lifted in those kinds of contexts?
Well, it's going along the way of with the question. It fits very well with the question of what happens to the BPS spectrum under our G-flow. So again, I don't know any counterexample where you have a lot more BPS states in the infrared than UV, but the question itself requires a lot of qualifiers because, and then that's, again, the whole, I mean, it opens door to many discussions. For instance, it's natural to expect, and I mean, I can give more arguments why BPS states tend to leave in pairs, first of all. So the difference between UV and infrared is going to be composed of certain paired BPS states. But in theories that we may keep in mind, it may also depend on the chamber structure, because the spectrum of BPS states depends on where you are on the moduli space, and BPS.
That's the wall crossing.
Exactly, that's the wall crossing story.
So this whole story is very different from this kind of story we're doing here. Because
no, it is in the same general direction, but it just requires analyzing, for example, what happens to the walls upon our G-flow, and I don't know the answer to this question. In fact, I was asking Philippe this question yesterday, and I believe there is a well-defined answer. I'm just saying nobody looked at it. So that's the beauty of thinking from this perspective, that it forces you to ask questions that we haven't asked before. So then, if you believe that there is a nice, reasonable flow of the wall structure and chamber structure, you can actually try to explore, even in examples, what happens to BPS spectrum in each chamber. And it seems that it gets smaller, in fact, by pairwise combinations. But A, there is no such general statement in the literature. And B, I don't know how to prove it in general, but that seems to be the case. So I don't know any counterexample to the fact where BPS spectrum would not be a good measure of space of states.
If you look at the wall crossing formulas, is there any hint or indication that they're going to give you this answer?
Well, wall crossing formula are kind of tangential, orthogonal to this, because they're part of the package, but they tell you how to go sort of horizontally before you start the flow, and then there is also the flow. So they two should combine in a much bigger picture that we haven't even formulated yet. So, but I'm glad that we're asking this question, because even thinking about it leads to completely different directions. Okay, so maybe I'll take 10 more minutes, because it's been a long day, and even though I believe I do have some time officially, I don't want to abuse it or use too much of it.
I've got like another half hour.
No, but I feel people are tired. So why don't I use like 10 minutes, and then we can continue more informally, or of course, if there is interest, I can continue definitely, but it's usually much easier to give talks than to listen. So I'll aim to use maybe 10-15 minutes to give you some evidence for this behavior of mu, and connect it to a couple of other things. So I spent quite a bit of time trying to say that yeah, so there are two questions here. One is whether, still talking about the mu behavior, whether it is possible to have mu infrared bigger than or maybe equal than mu UV, which is definitely counterintuitive, and as I claimed, if you use Moore's blot theory, you get topological obstruction to smooth our G-flow. So one question is, A, is it possible? And B, if it's possible, then what happens? In other words, what's the physics? Again, Moore's block theory would say that you definitely lose some of the assumptions. In fact, if you explore it a little closer, you see that you lose smoothness if this happens. And again, smoothness for us in physics often means phase transition. So the question is it really a phase transition, and what happens in this phase transition? What kind of physics? You can analyze this, and now I'll try to give you evidence that so far I try to give arguments that this is really hard to come by. I mean, I had to suffer really a lot and find some fairly contrived n=1 examples. They're not the most obvious n=1 supersymmetric RG flows. They're really based on some recent work and lots of conjectures, A theorem, A maximization conjecture, and so on and so forth, Seiberg duality conjectures that go into that. So they're not really simple theories on the one hand. And now I'll try to take this whole philosophy upside down and say that if I approach it from yet another angle, it seems that it's extremely easy to come up with such situations. And honestly, I don't know the resolution of this paradox. So now that I spent a whole hour trying to convince you that these phenomena are rare, interesting, once we start thinking about what happens in this phenomena, what was unnatural in the past hour will suddenly become extremely easy and natural, and again, it is going to be a puzzle. So that's yet another question to the list of questions I started with in the beginning. So the other way of looking at this that I have in mind is via ADS-CFT correspondence. So the way, of course, if assuming that our conformal field theories and in the infrared and IR have a large central charge limit, we all expect that in large central charge, many of them have some sort of ADS-CFT dual. So now I can repeat that same picture I already put on the board a number of times, where T is the RG time, and the way things will go is that we start with some ADS d+1 dimensional vacuum in the UV, and we go into ADS d+1 dimensional vacuum in the infrared. So they have different ADS radius. Radius of ADS is the only length scale, and depending on the dimension, it's typically related to inverse value of the central charge to some power. So in large N limit, which is what holography is supposed to do for us, this RG flow is represented as some sort of gravitational soliton in d+1 dimensions, interpolating between two values of the negative cosmological constant. If RG flow is supersymmetric, which is very natural to assume, and actually I was mostly tacitly interested only in those when I talked about supersymmetry, the soliton has to be supersymmetric as well. It has to preserve some number of supersymmetries. So actually in ADS-CFT, what happens is that this mysterious RG flow, if you believe in holography, now is just a normal soliton. In particular, the question of counting such solitons becomes a question of counting RG trajectories that we had in the beginning. So let's think for a second what this critical points could be. Typical gravity theory or supergravity theory has, of course, metric as part of its degrees of freedom, and it has gravitini, it has lots of other junk, and it has various scalar fields. So you have some scalar field potential V of phi. And when you try to study this, the soliton, it should solve equations of motion. So you have some Einstein equations coupled to various partial differential equations or just differential equations for other fields, in particular for scalar fields phi. So you have to solve some system of equations where as you evolve in this radial direction in ADS, which I call t, this RG time, you have evolution of metric d mu as well as all possible phi scalar fields as a function of t. So depending on gravity theory, there'll be various differential equations which control that, and you have to find solution, which means that you have the solid time. So now imagine the following situation. So let's re-ask here the question of what would be the coolest and most interesting phenomenon we're fishing so far. I alluded to the fact that there are these dangerously relevant operators being kind of the hint for interesting physics or something mysterious. So let's ask, how would they look like in holographic description? Okay. In holography, what happens is that various scalar fields in the supergravity have masses, so I'll call it, say, 1 phi squared, which are related to conformal dimensions of operators on a boundary via formula something like delta times delta minus d, or if I'm not mistaken, d is that still space-time dimension of the conformal field theory on the boundary. Therefore, what happens is that if you cross through marginality, if you go from irrelevant regime to relevant regime, it means that in the bulk, mass squared of some scalar field, which is dual to your operator, goes from positive to negative. And that's actually okay because it's okay to have tachyonic scalar fields and other fields and anti-de Sitter because of the cosmological constant. So m squared for phi and other guys is allowed to be negative. It's okay that it's less than 0, as long as it's bigger than or equal than BF bound. So I'll just call it BF squared, which is something like d minus 2 over 2, if I remember correctly, or something similar related to maybe d over 2 squared. And it's some negative number. So there is a little bit, you're allowed to be in a tachyonic range, but not too far. So it's ADS analog of flat space statement that we usually avoid tachyonic particles. So in this holographic dictionary, which is very standard, crossing through marginality, the phenomenon that we're interested in is phenomenon of going to negative mass squared. Okay? This is just part of ADS CFT dictionary. It has no assumptions. I'm not responsible for it. Blame Moldasana if anything goes wrong. Okay, so now let's see. Let's try to cook up some RG flow. If you're dealing with large number of supersymmetries, this potential for scalar fields and details of your supergravity theory is highly constrained. If you have fewer and fewer supersymmetries, you're allowed to write pretty much any V of phi. In fact, if you're interested in non-supersymmetric holography, write any V of phi. It may not have embedding in string theory, or maybe you may lose control, but that's the typical thing. In fact, if you have holographic duals to n equals 1 flows or minimal supersymmetry in other dimensions, even you can study ADS3, CFT2, you can write pretty much any V of phi. Some of those of you who like supergravity know this extremely well. So let's just cook up something. Now we start with the bottom-up approach from this point of view. Well, we want to have some flow, so we want probably to start with behavior of phi, which looks as follows. So we want to have some sort of potential which could be saying phi to the 4 potential, where we start at the top of the hill and roll down to a certain value. So that would be our RG flow. Each of these critical points of the potential will be some stable ADS vacuum. I can shift my energy so that none of these values V of phi is 0, so that they lead to negative cosmological constant. And then interpolating from one critical point of the potential to another will literally be gravitational soliton because geometry will back react. I have to solve equations, but again, it's not relevant. I can show you lots of detailed examples. It's not a big deal. It's very easy to solve for gravity back reacting to just a single scale. So let's assume that that's the case, that phi rolls down here. And in fact, I can start writing down the effective potential. So let V be something like phi squared minus k squared plus a constant, where we start this. Now, again, those of you who work with supergravities know that, and after all, if you're interested in CFT, which has more than one operator dual to phi, you have to have lots of scalar fields dual to other operators you have in the game. So let's introduce some other scalar field. And again, those of you familiar with supergravities know that there are usually 70 or 150 scalar fields, depending on which supergravity you have in mind. It has a scalar potential, which is a function of all of them. So let's reintroduce something else, some other scalar field sigma. And now you can easily ask the kind of question that we're interested in. We're interested in behavior where the effective mass for this other field sigma will be positive mass squared at these points. It will become flatter as we float down, and it will cross through m squared equals 0 line at some point, and it will become tachyonic, ideally still above this BF bound so that we don't violate unitarity or anything else, and ends up as relevant operator here. Now, first of all, you complained about the cartoon we had before, which now comes to life and becomes nice diagram in holographic description. Again, I don't know if it's largely an artifact or what, but you can actually track what happens with states.
You expect it to be a large N artifact, right?
Yeah.
You're somehow making a classical version of all that quantum stuff you didn't really know was
Yeah, in some sense, yes, exactly. But it's not that classical because now something weird is going on. And then suddenly we have control over this weird phenomena. And again, we're almost at a clash or puzzle. Okay, so suppose there is this field sigma, which starts with a positive mass squared, becomes flatter, and then goes down. So basically, I can easily cook it up. I just phenomenologically, what I have to find is a model where something like this happens. I'll say phi naught minus phi times sigma squared plus, say, sigma to the fourth to make things nice. Okay. I just roll you a bounded potential where I can easily adjust the value of this phi naught, where quadratic term vanishes, and as field phi continues to roll, so somewhere there is phi naught, as it continues to increase, I get into negative range, and that gets realized. Doesn't look very difficult. So what's going on? Didn't I just cook up? So all of us who are like phenomenological models, we never say there is obstruction to writing phenomenological model unless it violates like unitarity and this and that. And we construct Randall syndrome type models which supposed to reproduce physics from bottom up approach. So all I did, I followed same rules. I bottom up build a model which realizes this dangerously relevant operators here in holography.
You don't have the other space like when you have ADS cross S. You don't have the analog of the S over there?
No, I don't have analog of the S, but yeah, that's actually, I believe, part of the issue here, because, and unfortunately, people who do Randall syndrome and other bottom-up models, they also don't have analog of the S. And of course, this is an important problem because if we really want to be a little bit more rigorous, we have to construct first a DS supergravity. Then ideally we want to uplift it into 10-dimensional or 11-dimensional supergravity. And then, ideally, actually, we're supposed to uplift it to full-fledged string theory or M theory. This has never been done. In that sequence, there is no single model which from bottom up has been promoted that way. I mean, sometimes people suffer really hard to get from 4D supergravity to 7D supergravity, and they're coming short of 4 dimensions to get to 11, and not to mention including quantum, full quantum
I just think that
effects.
not all the things you can do this way can really be embedded in that.
Exactly, and I suspect that that's a big issue, but we have absolutely no control over that, and I think that's part of this. On the other hand, again, then it raises immediately a red flag to lots of other things which people do without fully upgrading and then knowing what the hell is going on. Because here, I can't even point, I can write for you lots of consistent phenomenological models like this, which reproduce dangerously relevant typologies, in fact, as many as you want. And I had so much difficulty finding them in field theory. And if I suddenly start thinking about RG flows holographically, yeah, things become nice and geometric and so on. And suddenly I have easy way of constructing it. It's okay. What's worse than that, you could suspect, oh, this is probably an artifact of the fact that here, what do I have? G mu and a couple of scalar fields. Maybe it's not a consistent theory of gravity. So let me try some supergravity at least with high amount of supersymmetry. What's worse is that this can be embedded in ADS3 supergravity with high amount of supersymmetry. So where I told you, and you thought would be the safest possible territory for dangerously relevant operators for this mixed theorem and stuff like that, and where people believe the strongest form of the C theorem, that's actually where I know one nice consistent quantum example of situation like this. So you basically scan through a bunch of supergravity potentials, you scan through all possible critical points, and you ask, is there something like this? Does this get embedded in any of those? And indeed, one example I managed to find is ADS3, which is dual to CFT2. So that's yet another big puzzle, and it goes complete opposite of everything I told you in the first part. So I think it's probably fair if I just stop here.
Can I comment on this last thing you were just talking about? Because sometimes people do, even black holes using only ADS and forgetting the S. Like you can do ADS3 but forget the S3 and the P4. And we know that is wrong because by doing the behavior of the stress tensor, people try to write down the effective value of C and then try to say there should be, the Cardi formula for that much C, that many states. So just looking at ADS3, people try to say, aha, I have a central charge C equals 6 and 1 and 5 in that case. So I should get e to the C root n states of energy n. And we know that is wrong because if you actually go back to see where those states come from, they actually come from the dimensional reduction of all that you could do on the S3 and the T4. So if you only keep the S, the central value of central charge there is misleading. Actually, there are no states there. ADS3 doesn't have any gravitational states. All the gravitational states of the CFT really come because the S3 and so on can be reformed, and the ADS reacts to that.
Mm-hmm.
But if you just take 3D gravity, as you know, it has no states. So what I'm wondering is it issue really handy if you make examples like this, where even the value of C itself is misleading because it's not part of the ADS?
Yeah, I totally agree. And again, I don't know a resolution of this kind of paradox. My feeling is that probably it's important to deal with fully microscopic models. Again, it's completely unrealistic. But there is one lesson that it teaches us. First, it translates the question in yet another language. And the real reason why I do this is actually to motivate or try to understand this nature of the physics. So here I was asking, can it happen? And I still believe that this is rare, even despite of what I showed you here in supergravity. But I would trust intuition about the physics in the following sense, that models of this type in holography have been used a lot for describing phase transitions in for example, superconductivity in ADS-CMP is exactly this model. I mean, it's just a version of it. And that's exactly where we're crossing through marginality. A is meaningful, and B causes phase transition. Chiral symmetry breaking in even Klebanov-Witten effect is same type. Double trace saturators in ADS-CFT, same business. All of these examples, even though of a different nature, they point in one direction that something happens. There is a phase transition. So that's why I trust kind of general lesson here. Those of you familiar with hybrid inflation model will realize that if T is a real time, this is the picture of hybrid. This is the potential of hybrid inflation, actually. And there are many more models in holography that, or even condensed matter related to that, we reach point in that direction. So I completely agree as far as trusting them fully microscopically, but physics-wise, I think they teach us a lesson. So that's the reason I put it on.
You were going to say something about what happens to the definition of mu in the case of marginal, when you have marginal, exactly marginal.
Oh, yes, that's right. Sorry. I kind of avoided that. Yeah, I can say a few words. I'm not sure how much details I should give. So and then it also depends on what we want. So very naively, so there are several layers to answer this question. One is replace equalities by inequalities. So that I already mentioned before. It's like zeroth order of answering this question. More meaningful is in the version of this Morse theory, each critical point has downward flows and directions, and also upward flows, which if we invert are precisely irrelevant directions flowing into it and relevant directions flowing out of it. So Morse theory is usually based on, in the cleanest form, on the study of generic height function and gradient flows where critical points are isolated points. So question what marginal operator is in this formalism means that there is not a critical point, but rather the whole critical set. So let me just describe it as a cartoon, like this circle, whatever it is, some conformal manifold. So from the Morse theory point of view, it's a situation where things are non-generic, and and then you have the entire space of fixed points. So moving on this manifold is changing values of marginal operators, marginal couplings, and out here. So in how do we incorporate this in Morse theory? That's precisely what Bott actually did. So this is the Bott version of Morse theory, which is now called Morse-Bott theory. And one way in which it is useful is the following. So if you start at some higher critical point, which is what in our approach we think as UV with respect to some C function, and suppose we flow, again, as this picture illustrates, perhaps in multiple ways, into some IR point. Oops, sorry, this is UV, IR. Yeah, and then I want to attach to this two indices, mu UV and mu IR, which are Morse indices of this point. Then the statement in Morse theory says that dimension of the space of flows flow lines between these 2 points is equal to mu UV minus mu infrared. So plus 1, there is always universal simple shift of the RG flow time t that becomes a parameter. So if you mod out by that or work with a reduced space, there will be plus 1 here. And that's the statement that, again, if everything is nice, if we're really talking about some space of couplings and so on, which has at least topology, then the difference should be positive. So that's the Morse theory beginning of the story, where it's positive or negative. And moreover, you have various refinements of this, which go by the name of Morse inequalities and Morse theorems, which say that one current polynomial of the entire space is something like sum of critical points q to the power, which is Morse index. So this is t star, mu of t star. So basically, if you know all the critical points in a given patch or section of your space, you can reconstruct its topology. So information about critical points is the same as knowing Betti numbers. Now, the only difference in this case of Morse block theory is that many of these arguments go through. The only thing you have to take into account this variety. And for instance, what happens is that this gets modified in a little trickier way. So, but again, it's possible to extract it. But this gets modified in a really elegant way. You basically multiply by Poincare polynomial of corresponding conformal manifold. So you still count how many things flow out of how many relevant operators there are here in this member of the family, but topology of this conformal manifold now gets in the picture, and that's kind of actually good for us because in physics we want to know what's the topology of the conformal manifold. So if you use this slightly more sophisticated technology of this block theory, we can get a handle on it. So anyway, there is a way to incorporate marginal operators, and again, one can go in further detail, and they basically end up modifying this formula sometimes. So if you translate this type of statements and modifications of the inequality, what you quickly learn is that you have to count both marginal and relevant operators if you really want this analog of Morse inequalities. Kind of technical wording, I'm not sure if it can be done. So.
Does it require the conformal manifold to be compact?
Yeah, it assumes that conformal manifold is compact.
That's pretty rare in examples.
Not really. No, I mean, it should be either compact or its natural compactification, because even examples that you think are non-compact, you should include point at infinity typically. Otherwise, you have to tell me, if you really think hard about it, we never say that we have no clue what happens to...
What we should say n equals 4.
Yeah, in n equals 4, I would say that it's basically fundamental domain of tau.
Right, but the point at infinity is really at infinite distance.
Well, but it's a cusp. I mean, it's a nice. I mean,
the
it's
weak coupling. The weak coupling.
Yeah. So that's a cusp. So that type of non-compactness is definitely allowed.
Another method of degree of freedom counting was this use of this thermal free energies.
Yeah. So again, I don't know much about. I tried to learn about examples in 3 dimensions. I don't know much about examples in other dimensions, and at least on 3D, it's not terribly convenient story. But do you have in mind 3D or 4D version?
Either one, 3D or 4D.
Actually, I don't know much about 4D version, so
It's not invariant that you're exactly marginal definitions. Just take n equals 4 at finite temperature and you compute at weak and strong coupling. And you get a
oh, that's right.
different
Yes,
number.
yeah. You have very different.
So if
stuff.
you put that extra constraint that you want it to be constant under marginal definitions, then it doesn't satisfy. On the other hand, it's almost by definition decreasing along flows, right?
By definition.
I mean, well, I don't know. It's basically computing the entropy as a function of temperature. So you either act at high temperatures. You're letting your temperature act as your cutoff, and so you're
Actually, there could be a counterexample to this inequality. Possibly, I'm not sure. Because if you apply to regular gauge theories, then you can constrain the size of the Goldstone-boson sector as a function of number of flavors. You know, you get this critical length. So if you apply to SU2 gauge theory with some certain number of flavors, then it would tell you that if you have less than 5 flavors, you get chiral symmetry breaking, and greater than 5, you don't. Now, people who are doing simulations now seem to claim that 6 flavor SU2 gauge theory has chiral symmetry breaking. So if that is correct, then that's a counterexample to this counting inequality. Looking for any evidence of a counterexample. I've seen a couple of papers in the last few months. Not commenting on the inequality, but saying that 6 flavor SU2 gauge theory has this phase structure.
I didn't mean by definition. I just meant intuitively it tries to capture exactly what you mean by the notion of coarse grain
Yeah.
increasing. So, but I
It's
agree,
sort of reasonable to
it's,
count it.
with gauge theories, it's hard to. Well, if there are no more questions for Sergei, thank him again.